Right. Namaste and welcome everybody to Bayesian neural networks and Bayesian linear models. So what we will go through basics of probability distribution first, and then we will go into Bayesian linear regression with MCMC. We are going to look at regression problems and classification problems, and then we will cover neural networks and so specialized training methods, specialized MCMC sampling schemes such as Langevin gradients and so on, and convergence diagnosis. So we covered this previously, but I'll go over this again. Why do we need probability distributions? Why is there a need to have a Bayesian model or probabilistic model? The major reason is one of the main reasons is so that you have some sort of uncertainty quantifications in predictions, some sort of uncertainty quantification in your results. It is so far with conventional machine learning methods, what we see is that we use gradient-based approaches, and when there's a prediction, we get one specific value with a set of weights and biases after training from a set of data points. With that, we do not get natural or robust uncertainty quantifications in the predictions. So the goal of Bayesian inference is capturing the weights and biases or unknown parameters of a model using probability distributions. So what are probability distributions? In visual terms, what you may have used, if you have no knowledge about probability distributions, you may have known about histograms. So a histogram is something that you construct from data. You have a set of bins and you report the frequency of that set of bins. So it's basically a histogram is a summary of data. It's a visualization of how the data looks. And with the histogram, you have some sort of, you can get interpretation of the data. And there's basic, you could see a probability distribution, something that emerges from a histogram, and it describes the data. And one such example is the Gaussian, or also known as the normal distribution. Here, what we can see is a normal distribution with interquartile range that is defined down here. And we have the median, you have Q1, Q2, the quantiles, and the interquartile range is given there. And then in the middle, what we have is the mean, right? And the spread of the distribution is given by the standard deviation. And the variance is squared of the standard deviation, squared value, and that is also a term used to define the variance, the spread of a distribution. What we see here is three Gaussian or normal probability distribution, univariate case, where we have the same mean, but different values of the standard deviation, which defines the shape of the distribution. Here we see the mean, different means and different variance. So you have this standard deviation squared, that's the variance. And as is noted here. And you can see that the means are different for these, and that is basically described by these two parameters. So the two parameters, the mean and the standard deviation, basically can be used to define a distribution. So what is a probability and likelihood from a statistics perspective? Probability is and likelihood in everyday languages are interchangeably used, but in the statistics and machine learning domain, they are well defined and they are not necessarily the same thing. They're not the same. Probability basically is the area under the distribution, for example, and of a specific within specific values. For example, here you can see for a case where there's lab rats, the weight of lab rats, so that's the data. And there's a mean and standard deviation. Mean is 32 and standard deviation is 2.5, right? So of that, we have Gaussian distribution. And if you want to say that what is the probability if you find if you pick a random lab rat, what's the probability that it will be between 32 and 34 grams. Basically, you take 32 and then you look at 34 grams in here, and then you look at the area. So you calculate the area. There are different ways to calculate the area. One of the known ways is integration. So you can integrate this to calculate the area. The other way is there's also numerical integration. And there are various other computational ways to integrate the area. So that's what you get as a probability. But if you want to get the likelihood is for a given value. For example, if you have a distribution mean of 32 and standard deviation 2.5. What is the likelihood that the mouse is, for example, weighing 34 grams? What's the likelihood? Then for that, the 34 grams, you look in here and then you look at the y-axis. So from the x, you look at where there's an intersection going to the y-axis, and that's basically what the likelihood value is. So probabilities are areas under fixed distribution, right? That's the notation how it's written. Probability given of data given a distribution. This sign basically means given a distribution. And that distribution is defined. There can be different types of distribution and different shapes of the distribution. And the likelihood is probability of the data. Likelihood is the y-axis values for fixed data points with distribution that can be moved. So these symbols, these notations are important to remember, the probability and likelihood. And we will move on to other types of distribution. We are going to come back to these later. So we have gamma distribution. So why do we, in a lot of cases, you assume that there's you assume a normal distribution when you have data, just real data, meaning negative and positive values, real decimal numbers. So normal distribution is usually used. But in cases where you certainly know that your data is a real number, for example, and it will always be positive, then that's when you use a gamma distribution, right? So as you can see here. So an example of a case where you should use a gamma distribution to model is weights, our weight in kilograms, because you know that the data will always be positive. Whereas the temperature of a day, that can be negative and positive, especially in cases in countries such as Australia. Not so, I mean, most of the cases, if you look at Sydney, you have positive temperature values, but yeah, there are some places there are negative values. So depending on the nature of the data, you choose the distribution. Okay. So, you can find, and there's also the inverse gamma distribution. And similar to you get the mean and standard deviation, you have two parameters in a gamma distribution. The alpha and the lambda, or sometimes the notation it's called alpha and a beta, depending on who is implementing and what notation is used. And based on different values of those parameters, your distribution will look in a different way. So in the first one, alpha and gamma is half, and alpha is 1. So similarly, you have an inverse gamma distribution, and that's how it is, different values. So these distributions, essentially, you can use Python and other programming languages to program these distributions and generate numbers out of these distributions. So hence, in Python, you have this random number, right? And when you have this, use something like random dot rand int, basically this line of code will pick a random number between 0 and 99. And dot random will pick decimal numbers. So you can run this code and see. And then you can have different, first it pick 81, and then random number, and then a vector of size 4, and other cases where you can get a matrix of integers, a matrix of decimals, and so on. There are other forms of distribution, such as the binomial distribution, which is used to look at other types of data. And we have, for example, here, gamma distribution, and the size and scale. These are the things that are, for example, the alpha and the beta. They are things that are used to give us parameters to the distribution depending on your needs. So what do we see here in the next piece of code? We see how you can use Python to generate data to develop these distributions and plot these distributions, and then you see the shape of these distributions. And as I said, you can obtain histograms. So the first set of lines here is just generally calling this random.rand and 200. And what we do is the data here, what we are doing to the data, we are then plotting the data. Yeah. So then we are plotting the data, and find the distributions. So one of the other things here that we are plotting. So first we are doing the normal distribution, then we are looking at the gamma distribution, and you give the shape and scale and looking at 200 data points. And then we're looking at new uniform distribution. So uniform distribution is that all the data points are equally likely. And what do we mean by equally likely? So first we get these shapes here, and we'll see the corresponding values in the slides. So we see the three distributions. First is the normal distribution, and we have the gamma distribution and uniform distribution. So, and you can use R to generate these distributions as well, using this set of code or similar code. Then in the case when you have more than one set of features, so what we're looking at so far were univariate or single features in data. If you have a set of features, then you're going to use a multivariate normal distribution if you consider that your data is normally distributed. So in a multivariate normal distribution, you look at the covariance matrix, and what the covariance matrix is. In the case of a uniform univariate normal distribution, you have a mean, but when you look at a multivariate case, you have a set of features in the data. So for each of them, you will have different means, but a multivariate normal distribution not just looks at the means independently, but it also wants to capture the covariance. How are the different features interacting with the data? So for example, like a very simple case is for a population of humans, or for a population of humans, one feature is the age and the other feature is the weight, right? So you would know that if it is less than the age is less than 2 years, then you are expecting a certain distribution in the weight values. And if the age is more than 2 years, you will have a different sort of weight values, right? So there's correlation. So such distributions can capture certain correlations. So not going further into spending too much time in here, just want to say that in Python you have the code, and this is the implementation of a multivariate normal from scratch, and basically using that code right there, and it is using a covariance matrix that it is getting, and we can run that and we assume a covariance matrix, run that, and can draw from the distribution. Similarly, we can use the R in the library maths can be used to generate. So so far what we are talking about would be useful for us in prediction problems where we want to develop models. For example, we want to predict what is tomorrow's temperature during lunchtime, or temperature for the whole year during lunchtime, or temperature for certain weeks during lunchtime. But if you want to develop a model which kind of tells you what type of cloth to wear, should you wear winter clothes or summer clothes? So if there's some categorical values, there's classification, then Bernoulli distribution and binomial distribution, these are the distributions that are used to model categorical data. And then in the case when you have a set of classes, like more than two, when you have binary values, then you have the Bernoulli distribution, and in n independent Bernoulli trials, if you have n independent Bernoulli trials, then that's a binomial distribution. But in the case when you have more than two, it's a not binary classification, but multi-class classification, then you are looking at a multinomial distribution. And this is essentially the equation for the multinomial distribution in its implementation is you can use NumPy and draw from a multinomial distribution. Right? So fast draw, if you can keep on running this, you have, okay, we are not seeding it with something else. So you get the same thing. And but anyways, you get different draws, and we are telling it that we want that many number in that many categories. So this is all that we have for probability distributions. And now we go into the next lesson about the basics of Bayesian inference, and then we are going to move into how are we going to use probability distributions to make a deterministic model, such as a linear model or a neural network, into a probabilistic model, right? So first thing first, Bayesian inference, and this is Thomas Bayes here, and he was quite interested in gambling and making money, very interested in those things, and he wrote a series of notes, and after he died, those notes were discovered, and Laplace and colleagues, they established the Bayesian inference and theory behind Bayesian inference. But what is Bayesian inference? It's basically it's a method that can be used for uncertainty quantification, and the inference is there. Inference is that. What does inference means in context? It means trying to find out something, trying to unveil a solution, trying to look for something given some information, some partial information, right? So it is, there are some terms here, such as uncertainty quantification, uncertainty in predictions. I have already mentioned it. What is uncertainty in predictions? For example, your conventional neural network or linear model will say that, okay, if what should be tomorrow's temperature based on temperature for a similar uh, weather patterns for the last 30 years, it will, let's say tomorrow's temperature at lunchtime is going to be 20 degrees. But that's an exact number it is given. But Bayesian linear model will say it will be 20 degrees, but with some uncertainty. That means it will be the mean value or the mode would be around 20 degrees or would be 20 degrees, but the uncertainty will be there, meaning it could be between 18 to 22 degrees. So rather than giving an exact value in a prediction, we are essentially giving a distribution. And in order to give a distribution, we need to have a probabilistic model, right? So what we are going to do, we are going to later first understand the theory and the motivation behind Bayesian inference, and then we are going to use that to develop a Bayesian linear model and a Bayesian neural network model. And in order to do that, we need to understand some of the key terms, such as the posterior distribution, the posterior probability distribution or the posterior distribution, the prior distribution or the prior probability distribution, and sampling methods, right? And evidence, relevant evidence. So these are the key terms to take. These are the things that are used to implement Bayesian inference. So it's a way to sample the posterior distribution with a sampling method, such as Markov chain, Monte Carlo method, which we will cover in this lesson, so that you could find out what the posterior distribution looks like based on the prior distribution, right? So that's what Bayesian inference is. And Bayesian inference can be used to find out unknown parameters in a model, such as weights and biases of a neural network model and weights of a linear model, such as logistic integration of a linear model, right? So the whole thing, Bayesian inference is based on conditional probability distributions. Okay, so that's a conditional probability distribution. The probability of B being true given that A is true. So that's the likelihood, and the probability of A being true, that's also known as the prior, and this is the marginal, the probability of B being true, and this is what is the posterior distribution, the probability of A being true given that B is true, right? So this is the Bayesian Bayes theorem, and attributed to get this guy here, but in his lifetime, he didn't really see that much implementation of this, and this is 17th century we look at. I've included a video at the end of this lesson, a nice YouTube video, gives a bit of history here about Thomas Bayes, 1701 to 1761. He died pretty young man, 60 years age is not much these days, but back those days, probably that was an achievement given the situation in medicine. Anyway, so the probability of A given B, we should note that the probabilities are between 0 and 1, right? It's not going to be a negative number. And it is using the multiplication rule, and that's the probability of I multiplied by the probability of B given A. And the Bayes law is probability I given B, and that's what's probability of I multiplied by probability of B given I divided by probability of B. So that whole thing, this whole thing here and here, this equation basically can be infused or implemented into an algorithm. And that's what we are going to do. What we are going to do, we are going to look at the gradient descent algorithm that has been used to train neural networks or linear regression models or linear models. And we can use this idea to fuse in that algorithm to develop a Bayesian inference version of it. Okay. So anybody has any questions so far? Okay, so here we have the Bayes theorem, and that's all that I said. There's prior likelihood data, right? And then we get the posterior distribution. So now you have a bit of a definition of the posterior distribution. For those of you who were thinking of the definition of posterior, yes, in the Bayesian statistics, it means this. But in everyday languages, people say, okay, the backside or the buttocks. They say, okay, that's the posterior, right? So that's in everyday language. It's probably not used that much these days. It's more of a term that is used more in the past. So it's not used that much everyday in everyday language. So the term posterior, I mean, it's something that you get after the distribution you get after a process, and that's the sampling process. So you're trying to find out the posterior distribution of the weights and biases, for example. The prior is some information that you get of the weights and biases, which you already know, right? And the likelihood is some type of, you can think of it as some type of fitness measure, some kind of an error function that's kind of embedded in a Bayesian probabilistic framework. So that's what there's the likelihood that you'll get is based on data, right? Data is X given by X, and theta. Theta is a set of weights and biases of a model, for example, right? And the data is there, right? You'll use that data to get the likelihood. You're going to insert the data in a model, find the predictions, and based on the given the theta, and you're going to get the likelihood. So in the beginning, this is, for example, your distribution, your prior distribution. After you do the sampling process, the prior distribution is changed, and this is what you see. So prior distribution is the distribution which you assume where there is no knowledge of the facts. There's no evidence. There's no data seen. When a model has seen no data, it's an untrained model, but there are just probabilistic weights and biases. You can say it has a prior distribution. When the model is trained and through some algorithm, inference algorithm, a Bayesian algorithm, gets a set of weights and biases, then that's that process will get you the posterior distribution, right? So an example of it in everyday things, right? So your friend asks you, what is, guess what's my weight? I ask you, guess what's my weight? Okay. And you give a value, right? And that value is based on, without you seeing what I have the weight that I have on the scale. It's just based on your assumption. And your assumption, your prior is not a guess. Basically, it's kind of expert knowledge. Every day we have our own expert knowledge and we build on that expert knowledge. Our brain has some sort of Bayesian computation. So in everyday terms, what Bayesian inference is, it's basically updating your expert knowledge, or your the better term of prior is not expert knowledge, it's actually belief. Belief is something you have without seeing the data, right? For example, some of us have believe in ghosts, but have never seen ghosts, right? We believe in a lot of things, right? Without seeing them. And then once we experience a ghostly figure, then you update that belief, right? Maybe you'll never see one, and maybe you'll see one or experience a haunting, right? So there are places in Sydney that are known for haunting, some history of hauntings, and there are tourist sites all around the world. So, anyways, so this is what it is. We are going to go into detail next with MCMC sampling. So, what is MCMC sampling? Is Markov chain Monte Carlo sampling, and this is the sampling process. This is the inference algorithm that is used to get the posterior given a model and data, right? So in the frequentist style, what we can say, what is close to a conventional neural network in the conventional neural network setting that you know, on conventional linear model. Let's say you started, you gave a set of weights and biases before training the model that you can think of as the prior, okay? And after you have trained, so there's the whole training process that you can think of the inference algorithm. And when you get another set of weights and biases that actually describes the data for the model, looking at the data, that set of weights and biases is changed. It's quite different from the initial sets of weights and biases that were guessed. So that was like the belief. And now the new set of weights and biases, you can think of that as the posterior, right? So going back to the same notation, we have in order, uh, as I said, in order, so to do that, we need to use an algorithm. And now we need to kind of slowly move away from that idea of training a neural network with gradient descent. But now let's think that we have a neural network and we want to use some other algorithm similar to gradient descent and iterative algorithm for training it. And such an algorithm is known as Markov chain Monte Carlo, right? So Markov chain Monte Carlo is such an algorithm. So how is it going to train the neural network? It is going to take a proposal, a set of weights and biases, right? And it is going to use a prior probability distribution and the model, which is the neural network in this case, or the linear model, and it is going to calculate a likelihood after looking at the data. So and it's going to update. It's either going to, what is this used for? What is the Bayes theorem used for? It is actually used for either accepting or rejecting that set of proposals, right? So going in here, we'll come back to that again. So very similar to a backpropagation algorithm or a gradient descent-based training of linear models or a MLE, you do this iterative procedure, right? So you have a set of propose a set of weights and biases, right? And execute the model. Execute model means you take that set of weights and biases. So let's assume, so you propose a set of weights and biases from a proposal distribution, right? Q is the proposal distribution, right? So you propose a set of weights and biases from a proposal distribution, right? And that proposal distribution can be just a Gaussian distribution. So let's say that we say a mean of 0 and standard deviation of 0.05, right? So it will generate a very small set of real random numbers, and that's a proposal distribution. That first let's say you initialize the neural network to weights and biases from -5 to 5, and then on them that you want to add some noise on it, right? So you can say this is a way to add the noise. from a proposal distribution. So now you have a new set of weights and biases, and that is known as that, right? So you had the X was your initial that was randomly assigned to your neural network. You took that set of X weights and biases, and you added real random noise to it. And that's the proposal distribution. So you get an X bar, right? So that's in iteration one or epoch one, right? You basically pass that to the neural network or the linear model given some data points, right? And this could be sunspot data, your iris classification data, and compute the predictions, the outputs for all the data points. And then you will compute the likelihood. And in this case, we will use the log likelihood. We'll go into the details of why likelihood, what is a likelihood, how a likelihood looks, how a log likelihood looks. And then we'll calculate the acceptance probability. And the acceptance probability is what is basically then you decide whether that set of weights and biases that you proposed before this, given and knowing the likelihood or some kind of a likelihood is some kind of an error or a fitness function. So you propose a set of weights and biases, you have a error function. And based on that information, either you're going to accept or reject that set of weights and biases. And that is done using Bayes theorem. And that's, you need to then calculate using Bayes theorem and acceptance probability. And based on the probability, you are either going to accept that a new set of weights and biases, if that's X bar will become part of the chain. So that becomes X is your current, X bar was the proposed. So your proposed replaces the current. If it is not accepted, then the current remains as the same. So you have the chain. So you can think of the number of samples from I to the number of samples. So you have a chain length. So 1, 2, 3, 4. So think of it as a vector, multidimensional vector, where I is the number of rows and the number of the columns are your weights and biases. So if for a model that has 1,000 weights and biases, you will you are going to do it 1,000 samples. Max samples is 1,000. So you have 1,000 by 1,000 vector. Just think of it that. And at the end, what you get when you do this procedure, you will get 1,000 mean and 1,000 standard deviation because you have a history of all the weights and biases that were either accepted or rejected, right? And when you are going to plot that, you are going to get a distribution of parameters such as this, right? Anybody has any questions, quick questions? Okay, thanks everyone. We will now go, that was more of an overview. We want a bit of abstract thinking where we look at the problem from a distance, look at the major components, and then we go into the main components, okay? So we go back to the equation. So now we know what are we dealing with. What is this? So data can be iris classification, sunspot prediction, abalone age, ring age prediction, theta, weights and biases for your neural network. Probability, this is your likelihood, and this is your prior. What is the prior probability given those weights and biases, where the model is not looking at any data? We need to calculate that probability. And what is the likelihood given the probability that we get here would give us the likelihood actually, right? And multiply that, those two likelihood multiplied by the prior, we get the posterior probability, right? And it's divided by the probability of the data, right? And that we can think of is the P data is the, sorry, my notation, it was supposed to be data here. It just says this data, D is the data. I'll correct that later. Sorry about that. So probability is the data is the marginal distribution of the data and seen as a normalizing constant, and it is ignored. So when you ignore it, we can put the equal sign basically because it's normalizing constant, and we put a proportionality sign there, right? So the likelihood is a function of the parameters given a model specific data, and it's a measure of fitness, as I said repeatedly. And the posterior distribution is constructed after taking the relevant information from the data, the evidence. So the data is also known as evidence, and this is an iterative procedure. And MCM using MCMC methods that implement Bayesian inference. It's a numerical approaches, and it is also known as marginalizing or integrating over the posterior distribution. So it's basically finding the area when you integrate. So it's you can see it is an area under the distribution. It's a numerical approach. So the reason we do this in a numerical approach is because for complex models such as neural networks and also for linear models, it is not easy to find do integration, just integration. You cannot just do that to find the posterior distribution because you have the data you have to take the data into account, right? And for different models, the data set will be different. So you need to have a computational approach. So why are MCMC sampling methods important? Firstly, MCMC sampling methods are not just constrained to machine learning, right? You can use them for any type of models. Firstly, machine learning, you can use it for linear models. You can call them Bayesian linear models. So MCMC is a sampling algorithm, and it basically implements Bayesian inference. That's why you call it Bayesian machine learning, if you put it into machine learning. You can call it Bayesian astrophysics too, if you're using MCMC sampling methods to find unknown parameters of some astrophysics models and geoscientific inversions, such as I was at the University of Sydney, and then we were having a set of geoscientific inversion problems, such as trying to find out for the last million years, what was the rainfall pattern like in a landscape, looking at landscape evolution models, right? So that's what it can be used for, and for reef evolution models. And I'll go into that towards the end of the lesson. So what is a Markov process? It's a uniform defined by its transition probability. And we have seen what this X and X bar. So it's a process which defines the probability of transitioning from any given state to another state. So from state X to X bar, what's the probability of transitioning from that state? So that's the Markov process. So it has a unique stationary distribution, and that's the notation for the stationary distribution given X. And a Markov process, the stationary distribution, unique process has a unique stationary distribution, but you can call it that given that there are two processes, two conditions that are met, right? That there must be an existence of a stationary distribution given by sufficient detail balance condition. Requires that each transition from X to X bar is reversible. This implies that for every pair state X and X bar, the probability of being in state X and moving to the next state must be equal to the probability of being in state X bar and moving to state X. So this is the definition of the distribution, the stationary distributions given the detailed balance condition is met. So a detailed balance condition is also applies in areas such as economics, for example, like so, when you have import and export, like you could say that it is following a detailed balance condition is there when the country's export is similar to the country's imports. When you're looking at two countries, which is two different countries, which is usually not the case, but sometimes it is there. But it is sometimes like if you compare India and China or export and import in Australia and China, export and import, that distribution, I mean, the net would be there, but you could look at the specific things at exports and imports in agriculture or in software or in IT. But even then, that's not usually there. So, but we need to get that to that condition needs to be there for MCMC sampling. If a detailed condition, a detailed balance condition is not matched, then we can say that the Markov chain Monte Carlo sampling has not converged. So for convergence, you need the detailed balance condition. So it's all these philosophical approaches we are going to see how it's implemented in the algorithm. It's very unique, very interesting. I found this as a computer scientist. 8 years ago, I was introduced to Bayesian stats thanks to my previous mentor, Professor Sally Cripps, who's a Bayesian statistician, and she loves Bayesian stats, and she kind of converted me into somewhat Bayesian, but I returned to move to UNSW, and I can say that I follow both forms of stats, frequentist and Bayesian stats now. So that stationary distribution must be unique, which is guaranteed by ergodicity. So we need to know ergodicity of the Markov process. So ergodicity is attained by when every state is aperiodic. That basically means when the system does not return to the same state at fixed intervals, does not return to the same state. And where every state is positive recurrent, and when the expected number of states for returning to the same state is finite. So in simple terms, in other words, an ergodic system is one that mixes well. So mixes well, meaning we are looking at the history of the accepted and all the accepted values of the weights and biases. So so we are going to implement the idea of the philosophy of the detailed balance theory when we are going to accept or reject new samples. So that is where the detailed balance is going to be implemented. And ergodicity, we will check by doing a convergence test. It's through convergence diagnostics to kind of know that the MCMC sampling process has converged. So in other, it is one that mixes well. You get the same result whether you average its values over time or space. So looking at example here, this is, for example, for a linear model, and you can think of it as one weight or value, right? And this is the number of samples you are using MCMC to, let's say, sample a linear model, right? A linear regression model. And let's say the problem is that you're trying to predict the sunspot, occurrence of sunspot. So looking at the sunspot data. So you have the whole history of the samples. So in this case, we had 5,000 samples. And these are all the accepted sample values, right? And then you plot plot this, and what we see is a multi-model posterior distribution. And here you have a univariate normal distribution. So this is the ergodicity. If you find the mean of the entire thing and you find the mean of groups, such as the mean from 0 to 1,000, mean from 1,000 to 2,000, mean to 2,000 to 3,000, and mean of this time period, 3,000 to 4,000, you'll have quite large differences in the mean. Whereas here, you are going to find smaller differences in the mean. So this system has converged. This has weight value has converged, whereas this weight value. So in the model, let's assume there were five weight values, and then we only looked at the first two weight values, and one of those weight values converged, the other one did not really converge. So sometimes you could have you train the model and then it converges. Some of the weight values will converge and some will not converge. So that is here's a case where what we see here is sampling, right? And this is from the MC tutorial paper that is given here. And throughout the lesson, we are going to use this paper, code from this paper and my other papers, some of them, but mostly this is the main reference point. And this video will become additional resource for this paper, the GitHub repo for this paper. So what we need to do when you are doing MC sampling, what happens, like, as you know, like when you train a neural network or train a linear model, in the beginning, there's very large error values, larger sum of squared error, then over time, then it kind of comes down and then it stays around there. So in MC samplings, in that period where there are very large values and it kind of comes to a lower value point, that's called the burn-in period. And you usually discard that period. So that's the burn-in period. And afterwards, then you consider the rest of them as part of the posterior distribution. So this is the posterior distribution, right? After discarding the burn-in period, right? So what is this? This is just the history, the plot of all the accepted weights of a single weight value, just a single weight value. This is just an example. So this type of plots, if you have a neural network of 1,000 weights and biases, you'll have 1,000 of these plots. If you have a linear model of 10 of weights and biases, you'll have 10 of these plots, right? So this is called the trace plot, right? This is called the trace plot. So here what we have is an example. What we see is how an example of how visualization of how a MC model is kind of sampling a posterior distribution over time. So that's how it is sampling a posterior distribution. And see, so as you can see, you know, like every time this is the trace plot. That's the trace plot, right? And when you sample more and more parameters, so the proposal distribution, if you have the right proposal distribution, so you have to tailor make the proposal distribution, right? So that's just a visualization there, and you have some videos on erdosity and detail balance you can see here. So moving on to the next slide, we are going to now go into more and more details. And before we go into the details, we would like to have a 5 minutes break. We'll have a 5 minutes break and then we'll come back to this. So I'm just going to end this session and we'll create a new session after this. Thank you.